This conference will now be recorded.
So, good evening, Deepa. Today we are going to learn spherical lenses. Excuse me. So, we'll learn first refraction at spherical surfaces. Then we'll be discussing refraction at refraction by lenses. Okay. So first, let us learn what are spherical lenses and what are the type of spherical lenses. I think this you have already learned in your 10th standard somewhat. Today we'll basically revise most of the part what you have already learned. I'll just and then we'll learn a new thing, that is refraction at spherical surface. Okay, so let us first learn what is spherical lens, etc. So a spherical lens actually is a piece of refracting medium. It is a refracting medium bounded by two surfaces. Bounded by two surfaces. And among those two surfaces, at least one has to be curved surface. At least one has to be curved or a part of a sphere. Then we can say them as spherical lenses. Okay. So what is the property we are going to study with the lens? That is refraction. Refraction. And we have learned what is refraction. Refraction is bending of light when it passes from one medium to other medium. Okay. So bending of light when it passes from one medium to another medium. That is refraction. So we'll learn or we'll discuss refraction by lenses mainly. So before that, we'll learn refraction at spherical surfaces, and from there we'll just get the input, and then that input or that result will be using for lenses. So spherical lenses have either both surfaces spherical or one of them at least has to be spherical and the other can be plane. Okay, so you might be thinking we are learning lens, but what is the use of these lenses? We most of us know the uses of the lens. See, we use microscope, telescope, camera, projector, and also simple glasses which helps us to read. Okay, very small letters, etc. Those are all lenses. So we have lot of uses of lenses, spherical lenses in our life. So spherical lenses are mainly of two types. What are those? One is convex and another one is concave. So this is actually the main two types. There are two types, mainly two types, convex and concave. Okay. So you might be thinking why we are saying this as spherical lens. Simply we can say lens. I'll come to that point, but before that also I can just tell you, see, the two surfaces of the lenses are actually part of some sphere. Okay, two sphere, part of two spheres. See, this surface is a part of kind of this sphere like this, and this is a part of the sphere. So if you draw those two spheres like this, then you get this portion intersection. This will act as a lens. Okay, the way you take the surfaces, you will get different types of spherical lenses. So mainly there are two types. One is convex, another one is concave. So what is convex lens? Actually, convex lenses are those spherical lenses which are thicker at the middle. See, at the center, these are thicker. This portion is thick compared to the edges. Okay, compared to the edges, the middle portion or the center portion is thick. So these kind of lenses are called convex lens, or in other words, this is bounded by convex surfaces. So that's why it is called convex lens. Okay, and concave lens is that lens which has a thinner portion at the center compared to the edges. See, the middle or the center is thin compared to the edges. So this kind of lenses are called concave lens. They have different name also. Another name, this is called converging lens. We'll learn why it is called converging, or you might know converging because when, okay, so I'll just tell you why this is called converging lens when I discuss about focus and etc. various definitions for the lenses. So more or less similar or same, more or less actually, see, there are few parameters which we need to know about lenses. So those parameters we have already learned in the previous classes. In this, see, there will be center for the lens, that is called optical center. Then you will have focus, principal focus. Okay, then you have aperture. All those parameters which we have learned for mirror will be here applicable for this type, these lenses also, spherical lenses also. Okay, so apart from these two primitive classes of lenses, we can have various other types of lenses also. Okay, various other types of lenses we can have. Okay, by the way, this concave lens is called even diverging lens also. Diverging lens. Diverging lens. Okay, so we can have various other type of lenses. See, you can see this is called equiconvex lens. That means both the surfaces are convex and they have same radius of curvature, etc. Okay, this surface and this surface are having exactly equal features, like center, they have equal radius of curvature, etc. So that's why this is called equal convex. Both the surfaces are convex as well as they are having same radius of curvature, etc. So this is called plano-convex lens when you have a convex surface and the other surface is plane. Then it is called plano-convex lens. You may know this. And interestingly, we'll see the plane surface has radius of curvature infinity. So that will have focus at infinity, as we have seen in case of plane mirror. Okay, when you have simply two convex surfaces constituting a lens, doesn't matter whether both are having the same radius of curvature or not. So that kind of lens is called biconvex or double convex or simply convex lens also. So biconvex lens and equiconvex lens, what are the differences? Actually, in this case, both the surfaces are having equal radius of curvature. But in this biconvex lens, both the surfaces may not have the same radius of curvature. Okay, this is called converging meniscus. Meniscus means you might know the. Okay, so meniscus will discuss it here, like water meniscus, mercury meniscus, convex and concave. See, water, if you just keep in a glass, generally you see the upper surface like this. So, and you'll see at this portion there will be water, but this portion there may not be water. Okay, this portion may not be water, may not be having water. So this kind of surfaces, so this kind of meniscus are called concave. And in case of mercury meniscus, like it meniscus will be like this. So this is called convex meniscus. Okay, so this is converging or convex meniscus, and you can see there can be concave meniscus also, as I have told here. So this meniscus, about meniscus will be discussing when we will be learning surface tension, etc. Now equiconcave lens. So similar to this equiconvex, when you have two concave surfaces having equal radius of curvature, then those are called that particular lens is called equiconcave lens. Then you can have concave, similar to plano-convex. One surface will be concave, another surface will be plane. You can have biconcave lens, both surfaces are concave, or you can have diverging. This is diverging meniscus. Okay. So these are things. Sometime in your exam there may be a question like, see, there is a concave surface which is in combination with a convex. So there can be a complicated combinations of lenses. We may take up few numerical examples as time comes. We'll take those. Okay. So now we'll learn some definitions. See, as I said, the spherical lenses are actually bounded by two surfaces, and those two surfaces are actually part of two different sphere. Okay, and lenses are actually transparent medium. They are made up of transparent refracting medium. So since these surfaces are part of two different circles, or sorry, two different spheres, so that's why this kind of lenses are called spherical lenses. And these two spherical surfaces, they have their individual radius of curvatures. So if you have a concave, sorry, convex, look here, in the convex mirror, you have two radius of curvatures. Among them, actually, see, according to sign convention, we'll see during our sign convention, like when I'll teach you sign convention in this case, actually very similar to the sign convention you have learned in case of mirror. So one surface will be having positive radius of curvature, another surface will be having negative radius of curvature according to our sign convention. And look, the center, exactly, the center of the lens is called center of the lens. See this is the center. Okay, suppose this is the center of the lens. So this is called optical center, as you can see from here. So this is called optical center. So here in concave also you can see that. And radius of curvature, actually the radius of that particular sphere, the spherical surface is a part of which is actually called radius of curvature. So the definitions are actually more or less same. And if you add these two centers with this line and then extend them, then you get what is called principal axis, similar to your mirror, principal axis. So you have two center of curvatures here and here. You just join them with a line and extend that line, you will get what is called principal axis. Okay, and one more important point is the focus. So you have, in case of spherical convex mirror, sorry, convex lens, you have real focus. Okay, you have real focus. That means what? If there are rays which are parallel to the principal axis, after refraction, what they do, they meet at a point on the principal axis, and that point is a real point. That's why this is called the real focus. Okay, real focus. And this is called principal focus also. The F1 is called principal focus. And you can see in this case, since this lens is transparent medium, and if this is equiconvex lens, from both sides it is actually symmetric. So you can have the refraction from this side as well as this side. This will be actually equivalent. So each point on the right hand side will be equivalent to the points on the left hand side. Okay, so you look here, the center of curvature. So this formula is actually valid for, like, F is equal to, sorry, 2F is equal to R, radius of curvature. This is valid for this spherical lenses or spherical surfaces as well. Okay, so this we have learned in case of mirror, but it is valid here also. So you can see these are the centers of the curvature, and you can use, since it is a transparent medium, you can use the lens from both sides. Okay, from both sides. So that's why when you have a focus over here from this center, this is OF1, suppose OF2. So if this is a focus, F2 is a focus, there must be a corresponding point on the principal axis in the left hand side, which will be having the same distance. Okay, at, like, if you just reverse the rays, then they will come and meet over here. So you have two foci. Actually these are called foci. Focus is the singular and foci. So this is actually plural number. So a lens has two foci. Okay, in case of concave mirror, so this is convex and this is concave, suppose B concave. So sorry, not mirror, this is concave lens. So in case of concave lens, what happens? After refraction, the parallel rays, after refraction, appears to meet at this point F1 on the principal axis. So this particular point is called principal focus. But this focus is actually a virtual focus, since we are seeing these lights, these rays are appear to diverge, not meet, appear to diverge from this particular point. So that's why this concave lens is called diverging lens, because the parallel rays after refraction will be diverging, and they appears like they are diverging from a point on the principal axis. So this is called principal focus. Okay, and in this case, in case of convex lens, since the rays are converged at a point on the principal axis, so this convex lens is called a converging lens. Okay, so this is called converging lens. Now we have almost learned all the parameters we should have learned, and there are few conventions or few properties of lenses. See, you might have already learned the parallel rays, the rays parallel to principal axis will be converging by a converging lens at the focus. Okay, so that's why rays will be meeting over here. In case of concave lens, they will appear to diverge from a point here. If any ray go through the center, then they will pass through without any deviation. They will pass through without any deviation. In case of concave, also the same thing. Okay, without any deviation they can pass. Okay, yeah. One more point is here. Since this concave or convex, so these lenses are actually made up of spherical surfaces. So when you have to measure angle of incidence or something like that, so you need to always, we know angle of incidence has to be measured with respect to the normal to any surface. So in this case, surface is spherical, so at any point you want to draw a normal. So what you have to do, you have to first draw a tangent to that point on this, like tangent at that point to the surface. So tangent to the surface at this point is this one, suppose. And now, see, since it is sphere, the normal will go always through the center. At any place you take, the normal will go through the center of the curvature. Through the center of the curvature. Okay, normal will go through the center of curvature like this. So anyway, so I hope you have understood what I'm trying to say. See, whenever there is a curved surface like this, so if I want to know what is the normal at this particular point, you have to draw a tangent and then draw normal to that. So this will be the normal actually at that particular point of that curve. Okay, since these surfaces are curved surface, you have to draw a tangent at any point, and then you have to find out the normal to that point. Then that will act as normal. Okay. So in this case, radius of curvature is the normal to any point on the spherical surfaces. So now, sign conventions for a spherical lens. The spherical, see, the sign conventions for spherical lens and the mirror almost same. Almost all the parameters are same here, similar to, very similar to mirror. So the sign convention also very similar to the mirror. You can look over here. Sign convention is actually denoted very nicely over here. Suppose you have an object over here. So this is a candle, suppose. So whenever, see, you can just do one thing. I'm just repeating it because I had already told you. You can think one thing, that you can just think Cartesian coordinate, two-dimensional Cartesian coordinate, Cartesian axis or Cartesian coordinate system. Okay, so you can take the vertical axis. So you have to just think the axis. You have to draw the axis through the optical center. So this is x-axis, suppose, and this is y-axis. Obviously, with positive and negative, you have to draw, and this side is negative x-axis. This side is negative y-axis. You just think in your mind, and then whatever distances you measure, you have to measure from optical center in both cases, whether it is concave or convex. So the distances you measure from optical center to the upside or along the positive y-axis will give you positive distances, and the distances you measure down, you are going towards negative y-axis, so it will give you negative distances. Distance along the y-axis is called actually height. So you can see upward you take positive height and downward negative height. So all the real images will be having at least negative height. All the real images will be having negative height, that we have seen in case of mirror also. Okay. Now see, in case of convex mirror lens. Oh, this is written as mirror. I'm sorry, this has to be written as lens. Actually the same. That's why maybe the mistake I have done. So this is concave lens again. So in this case, see, whatever distances in case of convex lens, see, your object is there in the left hand side. So the object distance you have to take, and we will be denoting object distance same as u, and image distance with v. Focal length will be denoted by f, similar to what we have learned in case of mirror. So what is u? U is object distance. Object distance. Then v is image distance. Okay, and f is focal length. Focal length. Okay, so object distance in case of both either concave or convex, you see, this has to be taken as minus u. Okay, image distance, that depends whether the image is real or virtual. In case of real images, the images will be in this side. So generally for real images, v will be positive. In this case, also the same thing. If the images are formed in the right hand side, then you'll get positive sign. But in this case, generally the real images will be formed left hand side. Okay, so like that you can find out. See, focal length in this case positive, it is real. In this case actually virtual, it will be negative focal length in general. Okay, so these are the things. So whatever distance you measure in the left hand side will be negative, right hand side will be positive. Okay, these I am talking about lenses here now. and upside positive, whereas down it will be negative. Okay, so this is all about sign convention. Now we'll try to learn how refraction happens in case of like at the interface of spherical surfaces. So far we have learned refraction at the plane surfaces, okay, but in this particular lesson we'll be learning refraction at the spherical surface. You might be a little bit surprised that what might be happening to the rules for refraction. What might be the case? Laws of refraction, how will they be applicable? Whether the laws of refraction will be applicable at the spherical interface or not. See, we have already discussed previously or in the previous classes. See, laws of refractions, they are almost universal. They can be applicable at any kind of surfaces. You might be thinking how it is. See, it is because any surface you take, suppose I take a spherical surface like this. So if I take a part of this surface, then that will act as a plane surface, right? Plane surface. If I take a big sphere, then I take a very small part of it. That will act actually that will be a plane, kind of this. Okay? If I take a very small part of a sphere. So that's why the laws of refraction will be applicable in case of spherical interface also. That means what we have learned? We have learned that angle of incidence, angle of refraction, and normal to the surface at the point of incidence will be in the same plane. Okay? And the second law we have learned, that is Snell's law. So that also will be applicable in this case. Okay? So now we'll just try to understand geometrically the refraction part. Since it is geometrical optics, we'll be using a lot of geometrical notions or concepts. Okay? So see in this figure, this NM, this is a spherical surface which is actually see this is the interface. Suppose this is the spherical interface and you have two medium over here, transparent medium. One is having refractive index N1, another one is having refractive index N2. So in this case, let us suppose that N1 is having less refractive index than N2. That means your medium at the left hand side is rarer and the medium in the right hand side is denser medium. We'll see what happens when refraction happens at this spherical interface. So this geometry can give you the answer for that. Okay, suppose in this case, look here, we'll we have a point object over here. Ray is actually getting refracted. So this is angle of incidence. You can see this is I. And as I said, at spherical surface, the normal will be always the radius of curvature, which is going through the center. Okay. Now you can see the ray is refracted like this, and here the point image has been formed. So O is the object and I is the image. Okay. This is the point image. So image of that particular object. And you can see this is the angle of incidence, and angle of refraction is measured with the normal. This is the angle of refraction. Okay. And radius of curvature for this particular surface is capital R. And according to our sign convention, see, if I just take the mi distance, this is image distance, which I can write as V. So this has to be taken as positive. And the radius of curvature, which is denoted by capital R. So this is the radius of curvature. This also is positive over here. Okay, this is also positive. Okay. And U is actually negative. So anyway, we are just going to see, we have already learned mirror formula. Mirror formula, we have learned that 1 by V plus 1 by U, this is mirror equation in fact, is equal to 1 by F. This we have learned in case of mirror. Actually, at this stage, see, in your 10th standard, you have just used this formula. You have used, but you have not derived it. Today, what we are going to do is, we are just going to derive this formula. This is called length formula, or equation of length. Okay. In fact, we'll be deriving few more equations for lenses also using this concept. Let's first do for this. Okay, so the rays incident from a medium of refractive index 1 to the another having refractive index 2. And see, in case of mirror also we have discussed that aperture has to be very, very small. Aperture means what? This height is called actually aperture. Okay, height of the lens. So this is called linear aperture. And you know, if you have this surface, so this is actually called angular aperture. Okay, the angle between the two ends. Okay, this is angular aperture, and this line is actually linear aperture. So here we have taken the aperture to be very, very small, so that the rays which are coming, those will be actually paraxial rays. And in that case, see, if this aperture is small, then mn can be taken as a straight line. This mn can be taken as a straight line or perpendicular to this principal axis. Okay. Okay, so we'll do here. So n is the actually mn. So this is the normal. See, mn is the normal on the principal axis. Now see, what we can do is, we can just take tangent of angle NOM. NOM. So this angle, you can in fact think of NOM triangle. Okay, if you just think this length, to be a straight line, MN line, straight line, then you can think that NOM or MON, whatever you can think that as a triangle. From that triangle, we are taking the angle tangent of that angle NOM. That means this angle. Okay, and suppose this angle is very small angle. So anyway, so tangent of this we can just, since it is a see right angle triangle, we can write in terms of the ratio of the sides also. So we can write MN over OM. Okay, now we are taking this NOM angle to be very small. Okay, small angle approximation we can use. What is small angle approximation? Tan of theta will be nearly equal to theta, or sine of theta will be nearly equal to theta if theta is very small. Okay, so in this case we are using that approximation. Okay, and what we can say, that tan of NOM is equal to nearly is equal to NOM. That means that particular angle is equal to MN by OM. If we require, we can do that. Okay, NOM simply can be written as MN by OM. Okay, if we require. You might be thinking, sir, why it is small angle approximation you are taking? Because I have taken the small aperture. So there will be rays very near to the spherical, principal axis. These are called paraxial rays. So these are called paraxial rays, and we are doing the experiment with this paraxial rays. Okay, so I can take another triangle. See this triangle NCM. NCM. This triangle I can take. If you take this triangle, you just take the tangent of NCM angle, NCM. This will be obtained by MN by MC. Okay, MC. So similarly, we can write this is nearly equal to NCM small angle approximation by MC. If we require, we can write that. We'll take another triangle. See the big triangle MNI. See this triangle MN and I. So from there we can write tangent of I. Okay, sorry. We can write NIM, angle NIM. So since it is geometrical optics or ray optics, we have to use lot of geometry to find out various formulas, etc. So that is what we are doing here now. So this will be similarly obtained by MN by MI. Okay, so you can write directly NIM angle is equal to MN by MI. Okay, so after doing that, what we can do for small angle approximation, as we have seen, we can write those angles directly also. See, in this case, we'll just go to the next section. Yeah, next page. Here, look, I'm just taking a triangle NOC. This triangle NOC. See this big triangle. I'm just setting it. This triangle. Okay. NOC, this triangle I'm taking now, and look here, I have to see, I have to go with the Snell's law. I'm just going to actually do sine I, N1 sine I. Actually, what I'm doing is, I'm just trying to get something like this. Okay, let us take this as I into sine R. This is what I'm just going to prove in this, at this particular interface. And from there we will be definitely getting the things over there. Okay, let us do that. See, in this particular triangle, for this particular triangle, look, this I, angle I is the interior angle, sorry, exterior angle. And we know exterior angle will be summation over this. Okay, I can write that. I is actually sum over NO M or NOC, I can write, plus so NOM plus NCM, angle NCM. I can write this. Let us see what we have got. NOM angle means what? MN by OM. And NCM means what? MN by MC. I can just write them. See, NOM, that means MN by OM. MN by OM. Here, NCM is MN by MC. Okay. So this I have got. Similarly, see, if I have to find out what is R, what you have to do, just take this as this triangle, sorry, this as exterior angle. Okay, this as exterior angle. Look what we can do. See, NCM is the exterior angle, that is equal to R. This is this two. R plus the angle NIM. Okay, NIM. So this implies, so you are taking this as a triangle now for NI and C triangle. For this triangle, see, NCM, this angle is actually exterior angle, and from there, what we can get that angle R will be is equal to NCM minus NIM. Okay, so NCM we know. What is NCM? NCM is again MN by MC, and NIM is actually MN by MI. Okay, this is what we know. Okay, so look here, by Snell's law, what do we know? N1 sin I is equal to N2 sin R. Okay, this is what is Snell's law. We will be applying this now. Okay. Okay, so if we do that, what we get? Let us see what we get if we do that. So sin I can write this, since this is a very small angle, I can write this like this. Okay. So once I do that, I can use See, N1 I'll keep as it is, N2 I'll keep as it is, but I can use this what is R and what is I can use those. So see, I'll just write from here. See, I is Mn by Om plus Mn by Mc. So N1 Mn by Om plus Mn by Mc. Okay. Similarly, N2 into Mn by Mc, R is this one, and Mn by Mi. Mn by Mc divided by Mn by Mi. So one good thing is that everywhere Mn is common, so I can take them up and then cross them if we like. Okay, so I can just do that. Mc, and this is N2 into 1 by Mc minus 1 by Mi. Okay, so now look, this Om, Mc, Mc, okay, these are all there. What we can do is we can just take them, take the similar parameters together. This Mc is there, two parameters are there. I can take them closer. Okay, let me take it N1 by Om. Okay, and I'll take here N2 by Mi here, since it is positive. Let me see, and then see, I'll just take this Mc over there, so I'll get N2 minus N1 over Mc. Okay, I hope you agree with me. So what I get N1 into Om. Okay, so I get N1 over Om plus N2 over Mi. This is left hand side. Right hand side I get N2 minus N1 over Mc. Okay, all right. So this is what I get. Now look, if I see, if I just let me do one thing, I'll just write what is Om, Mc, and Mi. So what is Mi? Look, Mi is V with a positive sign. Mi is V. What is Om? Om is nothing but minus U. And what is Mc? Mc is radius of curvature, R. Okay. So I can write those things. See, Om is nothing but minus U. Then Mi is image distance, that is plus V, and Mc also is plus R. So if you put all those things, see what I get, N1 over minus U plus N2 over V, and then here N2 minus N1 over R. So this is what I get. So if I just further simplify, what I get is N2 over V minus N1 over U is equal to N2 minus N1 over R. So this is actually the formula for refraction at the interface, spherical interface. So in this case, you can see that this formula can be converted to our known forms. Okay, but in this case, see, spherical surfaces, there are two transparent medium. See, two transparent, this is having N2 and this is having N1 refractive index. Okay, so for that case, we have got this thing. Okay, so you have learned, see, very simple formula, 1 by V minus 1 by U is equal to 1 by R. So that happens in case of AR. Okay, okay, let us see how we can get some idea if we just consider. See, we have, so finally we have got the formula. So this is N2 by V minus N1 by U is equal to N2 minus N1 over R. So this is the main formula. So this is N1. So suppose the first medium, that means the medium at the left is air, and this is some other medium having refractive index N. Okay, if we just take that approximation or assumption, then air means N1 is equal to 1. So N1 is equal to 1, N2 is equal to simply N. Okay, if we just put that, what we get, look, N over V minus 1 over U. Here you'll get N minus 1 over R. So this will be your modified formula for that case. Okay, so you have to use this kind of formula. Okay, so you can take off different things, like you have two objects lie in the rarer medium and image formed is virtual. So I'll take up various examples and numerical problems some other day on this particular topic, refraction at the interface of spherical interface. So there are many good things over here. We'll be actually taking up numerical examples, then you might be able to understand again better. And then, see, why do we learn this first? Because in the spherical surfaces you have only one interface, but in case of lens you have two interfaces like this. So what we have to do, we have to use that formula for both the surfaces. Okay, and I'll just give you a clue. When we will see refraction by lens, first we have to, what you have to do, we have to see the image formation everything over here for this particular surfaces, and the image formed by this surface will act as object for other one. Okay, and then finally one image will be formed. Obviously we will be discussing that in the next class. So so far here, I hope you should not have any problem to understand, but still if you have any question, Deepa, you can ask me here. Okay, do you understand this formula whatever I have derived? I have derived it very slowly. I think you have understood this. So, or see, you have to use the geometry. Okay, so this figure I have actually borrowed from ncert textbook. You can go through that. Okay, so here there are few assumptions. One is small aperture. Small aperture means this length, see, this length mn has to be taken as a straight line. Okay, straight line, small aperture approximation, and in that case small aperture means this angle also will be small angle. If this is small, obviously this angle also will be small angle. So this small angle approximation we have taken here, tan theta is equal to theta. Okay, and then the rest of the things we have used from geometry, okay, and trigonometry somewhat. So with that we have derived the formula. So from where we have gone, n1 sine I is equal to n to sin r. Okay, n to sin r. So this is Snell's law. From Snell's law, we have derived the law of. So this is equation of refraction at the interface, spherical interface. Okay, if you have separated by a spherical, two mediums separated by a spherical interface, so you will be getting this. Okay, so in case of C, you might be thinking, sir, can't we get uh, from, I don't know whether we should get from this particular formula whether we can get for plane surfaces as well. So in case of plane surfaces, see, radius of curvature is actually infinity. So maybe uh, okay, I'll just think over it and then tell you in the next class whether from this particular formula itself whether we can get the known formula 1 by V over 1 by U is equal to 1 over R. Sorry, 1 over F. Whether we can get this. Okay, I'll just discuss this. So in the next class. So Deepa, what is your doubt, and you can tell me now. If you don't have, then I can end the session over here. Do you have anything to ask me?